Welcome back to Talk Tensors, where we try to break down some of the really exciting machine learning research that's shaping, well, I guess you could say shaping the world.
Yeah.
And today we're going to be doing a deep dive into a paper that uses this really interesting approach for trying to predict where ships are going to go, their trajectories at sea.
Mm-hmm.
And it uses something called a spatio-temporal graph diffusion probabilistic model.
STGDPM for short.
There you go. Yeah, I was going to say, thankfully we have an acronym for that.
It is a mouthful. Mm-hmm. But, this research really, I think, hits a nerve because, the amount of traffic that we have on the seas, with global trade and everything,
It's
only increasing. It's just exploding. Yeah. So being able to predict, where vessels are going to be and, preventing collisions and things like that.
That's a big deal.
It's a really big deal. You think about the environmental damage from ships having accidents, and then the economic impact too, when things get delayed, and, it's a huge, huge problem.
Absolutely. Yeah, I mean, it's one of those things where, we don't really think about, all the stuff that we buy, where it comes from.
Yeah.
And, all the infrastructure, the systems that actually have to be in place to get those goods to us. And this paper really kind of focuses on, the uncertainty inherent in predicting vessel behavior, right? It's not as if, we can just say, well, it's at point A and it's going to go to point B. Captains make decisions. They have to interact with all these different, circumstances and other vessels. And so there's this whole kind of range of possibilities that we have to account for when we're trying to make these predictions.
Absolutely. And, there's this word that the paper uses, multimodality, which kind of describes that, right? Like there are multiple possible modes of how a ship might behave, and older methods, traditional methods, they got to struggle with that, right? Like especially when things got really busy and there were a lot of interactions, they weren't as accurate as we need them to be.
Yeah, and it seems like from reading the paper, a lot of those older techniques kind of simplified things a little too much.
Right.
Right. Like they were, averaging the movements of nearby ships, or, making assumptions about behavior that maybe weren't totally accurate.
Right. And it makes sense, right? Like when you're first starting out, you try to simplify things to make the problem easier to solve. But the thing that STGDPM kind of brings to the table is this recognition that interactions on the sea, they aren't uniform, right? Like they're very dynamic, and the context really matters.
Right, like a small little, fishing boat.
Right.
That's way off in the distance. It shouldn't be weighted the same as a huge cargo ship.
Right.
That's right next to you, and maneuvering in a way that is a little unpredictable.
Yeah, and those older methods, they didn't really have a way to account for that.
Right.
And then transformer models came along.
Yeah.
And, transformers, they brought in the idea of self-attention.
Mm-hmm.
And, that allowed them to kind of weigh different influences differently,
mm-hmm.
But they still had some challenges, like they weren't perfectly suited for this problem because, they have a hard time dealing with the fact that the data that we get from ships, like their locations and stuff,
it's not always regular.
It's not regular, right? Like the timestamps are all over the place.
Right.
And, the relationships between the ships are changing constantly. So it was a step in the right direction, but not quite there yet.
Right. So it's like they had some pieces of the puzzle, but they weren't really, put together in the right way to give us the full picture.
Right.
Right. And so that's, I think, where this STGDPM approach comes in. And, you mentioned SDGs before.
Right.
So can you kind of give us a high level overview of how this works? Like what's the big picture?
Yeah. So at its core, this paper is really doing something really neat. It's combining spatio-temporal graphs, which are, these graphs that represent the relationships between different objects over time.
Mm-hmm. And
it's combining that with diffusion probabilistic models, which are really good at, modeling uncertainty.
Right.
And they've reframed this problem of predicting a ship's trajectory as the reverse of a process where the uncertainty about the future kind of increases. So imagine like all the potential paths that a ship could take branching out, kind of like a cloud or something.
Right.
And STGDPM, what it does is it starts with this really blurry, uncertain picture of the future.
Okay.
And then it progressively sharpens it,
I like that.
by eliminating paths that are less likely. And eventually it arrives at this set of probable trajectories.
Okay, so let's break down that spatio-temporal graphs part a little bit.
Yeah.
So instead of just like looking at each ship individually, they're actually modeling the interactions between the ships as like a network that evolves over time.
Right.
Right. So what does that look like in practice?
Yeah. So at each point in time, they basically construct a graph, where every vessel is like a node in that graph. Mm-hmm. And the connections between those nodes, which we call edges,
right,
those represent how the vessels are interacting.
Right.
And the strength of those connections, it's not fixed. It actually changes dynamically based on how close the vessels are to each other.
Okay, so closer ships have stronger connections.
Exactly. And that's really important because, like we were saying, a vessel that's far away,
yeah,
it shouldn't influence, a ship as much as a vessel that's really close by.
Right.
Those older methods, they kind of treated all the nearby vessels as equally important.
Right. That was the problem.
And so that's a big step forward.
Right. And so within this dynamic graph framework, they introduced this thing called Trudge.
Right.
And so what is the role of this component?
Yeah. So Trudge is it's a neural network. Think of it as like the brain of the system.
Okay.
It learns how to understand the patterns in these dynamic spatial graphs. Mm-hmm. And it also takes into account, the history of the vessel's movements. Mm-hmm. And during this reverse diffusion process, which, we talked about where the future trajectory gets sharpened,
right,
Trudge is kind of like the editor. It's taking this noisy, uncertain prediction and it's gradually refining it into something that's much more accurate.
Okay, so instead of just getting like a single, prediction of the path,
right,
we're actually getting like a distribution of possibilities that gets more and more focused as the model kind of, refines its understanding.
Exactly.
Okay, and that sounds like a much better way to deal with that multimodality thing that we were talking about earlier.
Right.
Right, because it's not just like one or the other. It's like, well, here's the range of things that could happen, and here's how likely each one is.
Exactly.
Okay. Now, to really, I think, understand this contribution, it's helpful to kind of take a step back and look at, how vessel trajectory prediction has kind of evolved over time.
Right.
Right. Like where did those older methods kind of fall short, and how did the field progress towards this graph-based diffusion approach?
Yeah. So historically, the first attempts at vessel trajectory prediction, they often relied on these aggregation techniques. They'd look at a vessel and its neighbors, and they might just like sum up their velocities or average their positions.
Right. Just simple stuff.
Yeah, very simple stuff. But like we touched on earlier, a key insight that STGDPM brings is this recognition that interactions, they're not, all created equal.
Right.
So these early methods, they treated every nearby vessel with the same importance.
Right.
And that's obviously not how it works in the real world. It's kind of like trying to predict how a group of people are going to move by just looking at the average direction that everyone's facing.
Right. You lose all the nuance.
Yeah, you miss all the individual nuances and interactions.
Yeah, it's like trying to understand a complex social gathering by just measuring like the average noise level in the room,
Exactly.
Exactly.
You miss all the conversations, the interactions, all that stuff.
Right. And then, Transformers came along.
Right.
And Transformers, they brought in this idea of self-attention.
Which allowed them to kind of learn how to weigh different interactions differently.
Yeah.
And, that was a big step forward. But the way that transformers normally deal with positional information, like where things are in space,
right,
it's really designed for sequential data, things that happen in a specific order, like words in a sentence.
Okay.
But vessel traffic, it's not like that.
Yeah.
Like we were saying before, the timestamps are irregular. The relationships are changing constantly. So it wasn't a perfect fit.
Right. So even though transformers like offer more flexibility in terms of like, how much weight to give to different interactions, they still weren't ideally suited for like the really fluid and asynchronous nature of the data that we're dealing with here.
Exactly.
And so that's, I think, where these spatio-temporal graphs started to look promising, right? Because they're really they've been really successful in other domains. Like traffic flow and social networks where you have, lots of entities, lots of things interacting with each other. And those relationships are changing over time.
Right.
And so representing, ships and their interactions as a graph that changes over time, it seems like a very natural way to model this problem.
It really is.
Okay. Now, some of the early attempts to use STGs, in the maritime domain, they often focused on representing the uncertainty in like the final predicted location.
Right.
Right. And they use something called binary Gaussian distributions.
Right.
So can you kind of unpack that a little bit? Like what does that mean and what were the limitations there?
Yeah. So think of, those early methods as only being able to predict whether a ship was going to end up in like one of two broad zones.
Okay.
Right. So it's very coarse.
Right.
It's not giving you the fine-grained detail that STGDPM does.
Right.
So it could give you a sense of like, where the ship might end up. Yeah. But it couldn't really tell you about all the different ways that it might get there.
Right. Especially in response to all the other ships that are out there.
Exactly. Yeah.
Okay. And then, looking at kind of a related field, pedestrian trajectory prediction.
Right.
Which also has to deal with these really complex social interactions.
Right.
We saw the emergence of models like social GAN, which used generative adversarial networks, or JANs.
Right.
And those are really good at generating realistic data.
Right.
But they also had some limitations when it came to modeling this multimodal future behavior. So can you kind of talk about that a little bit?
Yeah. So JANs, they work by basically having these two neural networks that compete with each other. Mm-hmm. And that competition forces them to generate data that's really realistic. But sometimes they can have a hard time dealing with what we call discontinuous probability distributions. Mm-hmm. So imagine, a scenario where a ship has to suddenly make a really sharp turn to avoid an obstacle.
Right.
Right. So the range of possible trajectories in that case, it might not be smooth and continuous.
Right. It might be very abrupt.
Right. And JANs, they can struggle with that.
Okay.
And so that's, that was kind of a limitation of that approach.
Okay. Which brings us to denoising diffusion probabilistic models.
Right.
Which, they started out, being really popular in image generation.
Right.
But now they're being applied to these spatio-temporal graph problems. And so what is it about DDPMs that makes them, so well suited for this problem?
Yeah. So the real power of DDPMs is in their ability to model these complex multimodal distributions. Mm-hmm. And to explicitly deal with uncertainty.
Yeah.
Not just at the end point of the trajectory, but throughout the whole thing.
Okay.
So the way that they work is they first take the real data and they gradually add noise to it.
All right.
Until it becomes just pure random noise. And that forward process, that diffusion process, it teaches the model about the underlying structure of the data.
Okay.
And then the really important part is the reverse process.
Okay.
Where the model learns to kind of denoise this random data.
Right.
And turn it back into something meaningful.
Okay.
So because it learns this denoising step, it can generate this whole range of plausible future trajectories.
Right.
That reflect the uncertainty. And, this approach is really well suited for trajectory prediction because we care about both, where the ship is in space.
Right.
And also how that location changes over time.
Right. We need both.
Exactly.
Okay, so STGDTPM is basically combining like the power of STGs to model these interactions
with the uncertainty handling capabilities of DDPMs.
Exactly.
Okay, so let's get into like the nitty gritty of how they actually put this all together.
Yeah.
So what are the main kind of building blocks of their model?
Yeah, so the first key element is how they represent the interactions. And they do that using this dynamic spatial graph that's constructed at each point in time. Mm-hmm. And, like you said, each vessel is a vertex in that graph.
Right.
And the edges that connect those vertices are weighted based on how close they are.
Right.
So specifically, the weight is inversely proportional to the square of the distance between them, but only if they're within a certain range. There's a threshold,
right,
which they call tau, mm-hmm. and that allows the model to focus on the interactions that are most relevant.
Right.
The ones that are close by.
Makes sense. Makes sense.
Yeah.
The ships that are close to each other are more likely to influence each other's movement.
Okay. Now, how does this overall STGDPM framework, how does it use these graphs within the diffusion process? Like, what does the training look like?
Yeah, so the framework, it basically operates in two main stages. There's the training stage, and then there's the prediction stage.
Okay.
So during training, they use this thing called a conditional diffusion model.
Yeah.
And they feed in the historical trajectories of the vessels.
Right.
And the sequence of dynamic spatial graphs, that represent the interactions. And then the model takes the actual future trajectories of these vessels.
Right.
And it progressively adds Gaussian noise to them.
Okay.
Over a series of steps. And this triunit network that we talked about, it learns to reverse this process, to take a noisy trajectory and predict a slightly less noisy version, eventually leading up to an estimate of the original clean trajectory.
Right.
And the way that they train it is they minimize the difference between those denoised predictions and the actual future trajectories.
Okay, so it's kind of like a game where you're taking the true data and you're messing it up.
Right.
And then you're saying, okay, model, try to undo what I just did.
Exactly.
And then through that process it learns.
Right.
Okay.
Yeah.
Now, when it comes to actually making a prediction for a new scenario, how does the model generate those future paths?
Yeah, so for prediction, they start with basically just random noise.
Okay.
Which represents maximum uncertainty about the future.
Right, because we don't know anything yet.
Right. And then they iteratively apply this learned reverse diffusion process, that we talked about before. And they condition it on the trajectories that they've observed,
right,
and the dynamic spatial graphs.
Okay.
So at each step, the trajectory, it takes this noisy prediction and it refines it, making it more like a realistic vessel trajectory. And because the initial noise is random each time, you can actually generate a whole bunch of different possible trajectories.
Right.
Reflecting that multimodality.
Right. So it's like running a bunch of simulations of the future.
Exactly.
Okay, very cool. Now you mentioned earlier that Trudge has this U-shaped architecture.
Right.
Can you talk about what are the key components within that network that allow it to learn these denoising steps? Yeah.
So it uses what we call a U-net-like structure.
Yeah.
And that's become really common for, tasks where you're taking in a sequence and outputting a sequence.
Yeah.
So it's got this downsampling path that kind of extracts features from the input.
Okay.
And then an upsampling path that reconstructs the output.
Okay.
In this case, the less noisy trajectory. Yeah. And a key building block within that U-net is something called a residual block. And that incorporates this module called dynamic GraphCom.
Dynamic GraphCom. Okay, and what's the role of that module?
Yeah, so dynamic GraphCom, it's specifically designed to kind of fuse the spatial information from the graphs with the temporal information from the trajectories. So it first normalizes the adjacency matrix.
Right.
Which kind of helps to make the learning process more stable.
Okay.
And then it performs this spatio-temporal aggregation.
Okay.
Which allows information to flow between the vessels.
Okay.
Over time.
Right.
And then that information is transformed using learnable parameters, weights and biases, and combined with the original features through a residual connection. And those residual connections are really important because they allow the network to learn these really complex patterns without losing important details.
Okay, so it's not just like looking at each vessel movement individually. It's really kind of capturing like the how the interactions are influencing the movement over time.
Exactly. Yeah.
Okay. Now the paper presents some really cool experimental results.
Right.
Using real world AIS data. So what kind of data did they use, and how did they evaluate the performance of STGDPM?
Yeah. So they used real automatic identification system, AIS data,
right,
from two really busy port areas in China.
Yeah.
Kiev Feeding Waters and Tianjin Port.
Okay.
And this AIS data gives you detailed information about each vessel, like their ID, their timestamp, their location.
Right.
And they pre-processed it. They cleaned it up a bit.
Right. Always got to do the data cleaning.
Always.
Yeah.
And to measure how well the model was doing, they used two common metrics in trajectory prediction. Average displacement error, ADE,
IDE.
and final displacement error, or FDE.
FDE.
So ADE, it measures the average distance between the predicted positions and the actual positions.
Okay.
Over the whole trajectory. And FDE just focuses on the distance between the final predicted position and the actual final position.
Gotcha. And they evaluated predictions over different time horizons.
Right. Yeah, they looked at 5, 10, and 15 steps into the future, and each step was 10 seconds.
Okay, so 50 seconds, 100 seconds, 150 seconds.
Exactly.
Okay.
And because STGDPM is probabilistic, it gives you a distribution.
Right.
They use this best of n strategy where they generated multiple predictions, and then they chose the one that had the lowest error.
Okay.
And that makes sense because the model is able to give you multiple plausible paths.
Right.
And so you want to see which one is the most accurate.
Okay. And so how did STGDPM compare to other, state-of-the-art trajectory prediction methods?
Yeah. So the results were really impressive. Across both of the data sets and all the time horizons that they looked at, STGDPM consistently did better than a bunch of different models.
Wow. Okay.
Including things like LSTM, C2-sec models.
Right.
Those are kind of classic. And then also, some more recent graph-based models like social STGCNN and social JAN.
Right.
And even another diffusion-based model called MINDI.
Okay.
And the improvements were statistically significant, meaning that it wasn't just, random chance.
Right.
It was a real improvement.
Okay, that's huge. Now, the paper also provides, some visual examples of the predicted trajectories compared to the actual ones.
Right.
What did those qualitative results kind of reveal? Like, what did those pictures tell us?
Yeah, so the visualizations, they really show you the power of the model. So in situations where you have vessels making turns or changing speed, STGDPM's predictions were much closer to the actual paths than the other models.
Okay.
So those simpler models, they often had a hard time predicting those sharp turns.
Right.
And that would lead to, pretty big errors.
Right.
But STGDPM, it was able to capture those dynamic changes much better.
Okay, cool.
Yeah.
And you mentioned this earlier, but one of the key things that this model is able to do is to handle that multimodality.
Right.
Right. And especially in situations where you have, maritime rules like the starboard rule, that kind of dictates, who has the right of way.
Exactly. Yeah.
And so, were there any examples in the paper that really kind of illustrated that?
Yeah, they showed, some examples where STGDPM was able to generate multiple possible actions in interactive scenarios.
Okay.
So it could predict that a vessel might either continue on its current course or it might make a maneuver to yield to another vessel, which is consistent with the maritime regulations.
Right.
And, that ability to model those different potential behaviors, it's really important for real world systems.
Absolutely. Especially if we're going to have like autonomous ships.
Right.
They need to be able to understand, not just like the rules of the road, but also like what other ships might do.
Exactly.
Okay. Now, the paper also includes some ablation studies, which is where they basically, remove different parts of the model.
Right.
And they see how that affects performance.
Right.
So what were some of the key takeaways from those experiments?
Yeah. So those ablation studies, they really highlighted how important each part of the model is.
Okay.
So when they removed the UNet structure or the dynamic graph conv module or the residual connections,
right,
the performance dropped, significantly.
Oh, wow. Okay.
So that tells you that each of those components is really important.
Right. It's not just like, one thing that's carrying the whole model, right? It's the combination of all these things working together.
Exactly. Yeah.
Okay. And they also explored, how that interaction ranged, how that affects things.
Right.
So what did they find about, how far away vessels need to be from each other to really have a significant influence?
Yeah. So they experimented with, different values for that tau parameter.
Right.
And what they found is that there's kind of a sweet spot.
Okay.
So if it's too small, then you're missing important interactions.
Right.
But if it's too big, then you might be including interactions that aren't really that aren't really important.
Right.
Then that can actually